Hello and welcome. Here we are, another day. Let's do about. Oops. Let's just make sure everything's working before I begin. Forgot to change the title. So, whoops. What's that? I don't know. I just clicked. Okay. Let's see how we're doing here. Hello, hello, hello. Oh, it's so loud. Jesus. Okay. Stream is good. Everything's good, man. Looks good. Okay. Cool. Cool. All right. Yeah, it's great. It's already been a minute. It's already been a minute of me just stare at the screen here. Okay. This question was tough. I was working on this the other day. And I kind of got stuck on it, sort of. How are we doing here? A little bit of buffering, quite a bit of buffering actually, substantial buffering. Oh man, okay. You know what? Let me try something here. Okay, does that help? That's a lot of buffering. May have helped a little now. Did not help that much. Okay, give me a minute here. That's not good. Yeah, that's not good. What's going on there? I think we're gonna try something here. Okay. Is it still working? Let's see. So I don't know if it's still working. Let's see. Okay. Hello, hello, hello. Still going. It's still working. Okay, it looks like it's working. Okay, it's just a lot of buffering. Hello, hello, hello. All right, I think we're okay here, but let's see how this goes. Still going. 3.5 minutes. All right. It's still working. Okay, it looks like it's working. Okay, it's just a lot of buffering. That's a crazy amount of buffering, man. Yeah, I don't know why it's struggling so much all of a sudden today. I think it's going to be okay, but it's very disappointing. Frustrating, disappointing. Yeah, that's not good. I could see it's not. I don't know what's going on there. I might have to look at that later, figure out what's going on. All right, anyway. So this is a tough question. Challenging question. Largest submatrix of the rearrangements. Given a binary matrix of size n by n, you are allowed to rearrange the columns of the matrix in any order. Return the area of the largest submatrix within matrix where every element of the submatrix is 1 after reordering the columns optimally. So I got stuck on this the other day. What they're saying is you can reorder columns, and you've got to find the largest subarray, submatrix that has all ones in it. So I have to admit, I looked for a hint regarding this question, and it was not that hard to figure out after I got a hint. So this is very similar to the histogram-based questions where you're just trying to find the largest subarray, submatrix rather, largest area submatrix. The difference though for this question is that because you can move the columns around, it's almost the same approach. It's just now for each row, you can sort the row in descending order and move left to right, and get the basically get the area of your histogram, the area represented by the histogram much more efficiently. And so it's actually like a very straightforward question in that regard. I think there is something here that's kind of tricky. Yeah, I think the way I'd like to do this is I was thinking of okay, I think I know what to do. Okay, yeah, I was thinking of using frequency maps and counting sort to do this more efficiently. And I think I can actually do it more efficiently. Yes, I can. Okay, so we'll do this. We'll go through the answer here. I am pretty annoyed though at the extremely I don't know what's going on, man. The buffering is no fun. Okay, so we're okay. Yeah, it's no fun. Okay, so let's do this. Yeah, I have an idea. Okay, we're gonna do this. So we're gonna have thread local of the heights. This is gonna be an integer array, heights, and it's gonna be 100,001, initially empty. And then we do another thread local frequency, and this is also 1,001, 100,001. Okay. So constant m equals matrix dot size, and then n. So rows n columns, n rows. 0 dot size. Okay. Now, the way this is going to work, we're going to do for each row, so we're going to say const auto row in matrix. We're doing now. Still more buffering now. Yeah, it's struggling. It's really struggling. That's no fun. Okay. Well, we'll just keep trying, I guess. Just keep going. For each row, we're going to take the heights, say int I is 0, I is less than row dot size, commit I, which is really n in this case, I is less than n. I'm going to say heights of I, it's going to be either incremented by 1, or it's going to be set to 0. And this is going to be heights of I, not heights of I, row of I. If row, yeah. So if row of I is 0, then I think we just say, quite frankly, you could just multiply. Yeah. So it's 0, then we get 0. If it's 1, then we get, I'm actually not sure. I think this is more efficient, actually, to do it this way. Okay. So that's how we're going to modify the heights. And then we would say the frequency is you're always going to change the height. So the frequency of, let's say const int current h heights I. Okay, frequency of current height is going to be decremented. And then frequency of heights of I is going to be incremented, which could be 0. Yeah, I'll just have to remember to only, yeah, we could do it this way. That's fine. We'll just reset it here. It's fine. So we get our frequencies. And now, once we're done with that, we want to go from int I equals 0 to I is less than. So this is going to be the number of rows, actually. The size, so how much the frequency is bounded by the number of rows. It could be equal to m, though. It could be equal to m. And I also need to remember to start at 1. Just kind of subtle. But result is going to be the maximum of result. And it's going to be I times prefix, which int prefix is going to be 0. Prefix equals plus equals frequency of I. And then it's going to, take I times this, not I times the prefix, but I times the prefix is right. Yeah, so it's actually going to go backwards. Excuse me, it goes backwards. So m greater than or equal to 1, decrement I. So this is kind of subtle. But we add the number of heights that are on the larger side and decrement down. And if those are, actually, I should even optimize this slightly. Just int largest frequency or highest, greatest height. I can optimize this slightly. Just greatest height, student max. And heights. Okay, in which case I don't have to start at m at each point, which might optimize things quite a bit, actually. Yeah, I think so. So this could be actually kind of inefficient if I do it this way. Trying to use a counting sort instead of using a standard sort routine. Let's see how we're doing here. Still buffering. It's like mega buffering. It's no fun, huh? Yeah, that's no fun. Okay. So there is an issue here. The issue is that kind of have for each row, I was thinking about using a frequency map, but actually that's not really a good idea because the greatest height could be very high, which would be kind of an issue. Well, if there are a lot more rows, let's say there are like way more rows, 3/4 rows compared to 1/4 columns or something. Yeah, I think it's actually fine because this is only going to happen. Well, it happens for each row, right? Hmm. Yeah, that is actually a little bit awkward. I don't think I should do it this way. No, I don't think so. Ooh. I was trying to optimize using counting sort instead of the standard sort, but actually this could be kind of bad. Yeah, this could be kind of bad. Thinking about it again. Oh, that's a good question, actually. It's not really the memory that's the issue at this point. It's the shoot. The height could be very high, in which case I would need to. It's very awkward. Okay. That is very awkward. Ooh. Yeah, I'm not so sure about this one actually. I think a little bit harder about it. No, I shouldn't do it this way. No, it's not yeah, it's a little bit awkward. It's a little too awkward to do it like this. Okay. All right, that's fine. Not the worst thing in the world. Not great, but not the worst. Okay. So instead, we won't use frequency. We'll just say heights. Yeah, and we'll just say sort heights. That's fine. Okay. Oops. I have another idea. Yeah, I was trying to optimize for this, but that little doesn't quite work. All right, this is just gonna write in the sorted heights and then sort them afterwards. Just use a simple. Oops. N is the N is the number of columns. So it's the row length. Okay. Sort them descending order as well. Well, yeah, descending is probably the right way to go. Wondering. Yeah, it's easier to do descending. Yeah, it's easier. I could also just reverse it instead. Yeah, it's probably better to do it this way. I was gonna say I could. I wonder if I could do this actually. I could also reverse it at the end. I think it's better to. I think it's better to just use a different sorting primitive. Yeah, and then we just say. Don't need that anymore. And we're going to say results equals std max result of I times sorted heights of I. I think it's I plus 1, by the way. Yeah, I think it's that simple. I mean, I wanted to do something a little bit different, but that's all right. Yeah, the other approach actually kind of has some issues. How are we doing with regard to buffering here? Still a lot of buffering. I don't know. It's really. Oh. Huh. What happened here? Hmm. Mm, hmm. Hmm. Got 5? Huh? What? I might need to debug this. What is going on? Four three one zero zero. Should be 6. Yeah, got up with 6. Although actually, this should just be 10101. Why 43100? 4 there? 43100. Oh, I know it's wrong. That's my mistake. Totally goofed that. Right. That's subtle. Duh. Yeah. I was like, what did I do? What did I do, man? Okay. Compiler. We'll just use stdfill, I think. I think it optimizes correctly anyway. Okay. I was like, I'm sure my answer's fine. Okay, I've spent a lot of time on this question so far. Still buffering? Kind of still buffering, I think. So to kind of review, yeah, I spent a lot of time on this so far. To kind of review the answer here, I'm going to go ahead and submit this. I think this is right. I think this is probably pretty fast. I'll explain the question and the answer in a moment. Okay. Oh man, it's not as fast as it could be. Shoot. That's a bummer. That's a bummer. Shucks. I'll explain in a moment. Let's do this. Okay. It's fast, but it's not. Oh, shit. It's fast, but it could be better. All right, let's do this. So, quick note on the question. Largest submatrix of the rearrangements. Given a binary matrix, size n by n, you're allowed to rearrange the columns of the matrix in any order. Return the area of the largest submatrix within the matrix, where every element of the submatrix is 1 after reordering columns optimally. So they give you an example. So here's one column, here's another. And if you move this one over, then you can get this submatrix of size 4. So return 4 here. And then, here's some other examples. The solution's actually pretty straightforward. What you can do is use a histogram approach. So you would keep track for each column of the runs of the ones that you see. And then you would basically try to figure out what the largest rectangle is you can get on that row by row. So like here you would have a 1, and a 2. Or here, well, 0, 0, 1, 1, 1, 2, and then 2, 1, 3 would be sort of like the heights of each column. And then if you sort the heights, then from descending, so in this case you get 3, 2, 1 at the bottom. What you can do is say, all right, that would give me because I can rearrange the columns, I can basically move my histogram elements around in that way. So you get 3, 2, 1 down here. And then you could say, okay, the largest rectangle is going to be either 1, 3, or 2 2s, where the next one is 2. So 2 2s, or 3 1s, where the next one is a 1. 3 1s, so 1 3, 2 2s, or 1 or 3 1s. And you just multiply your index I plus 1 by whatever value you have in the histogram. And that allows you to efficiently determine the rectangle size, which is what I did here. And then I used some optimizations to try to utilize the memory more efficiently. However, this isn't as fast as I was hoping it would be. I was hoping this would be basically the fastest solution, but maybe not. I throw it in the, yeah, it's pretty close. It's really close. I'm gonna throw it in the the assistant to see what I get here. Okay. Correct and efficient solution to 1727. I don't think it's 1727, by the way. Oh, it is. Okay. It's like, it's so close. I bet if I keep it submitting it, it'll probably give me the 100%. All right, histogram-based approach for the greedy strategy. Yeah. Height accumulation, optimal rearrangement sorting. Sorting, there's the heights, multiplied by -1, and by n log n. Okay, space complexity. Thread local arrays, size n. Store intermediate data, input matrix is not modified. Oh, maybe I should use the input matrix directly. I'm not sure if it's actually faster or slower. We'll keep trying. That's one optimization. Okay. Okay, now looking for micro optimizations. Maybe I could just reuse first 2 rows instead. Thread local storage. I think. Using the first 2 rows is indeed the standard space optimization technique, often superior to thread local arrays. Okay. In place, reduce when the space required. Okay. Most optimal solutions modify the input matrix directly. Okay. Let's see. Cache locality, okay. Okay. So we'll just do it in place. That's probably actually what the I tried to be so clever about this. I tried to be so clever about this. You don't need to do it like this. Okay, we're gonna do for each row, we're gonna say row of I is equal to row of I minus 1 and plus 1 or 0. And then we're not gonna have sorted heights. And we're gonna do not row of I minus 1, row J minus 1. Previous row. Yeah, okay. I, J. Okay. Let's try this way. All right. So we're going to say row of J is going to be matrix of j minus 1 by I minus 1 j. Okay. And we're going to do one by one. And we just take std accumulate of matrix 0. So we'll just pre-process the first array to keep things simple. The first row, rather. And then now we can just sort of sort row, decreasing order. And then use j. And this is just going to be row. Okay, how about this one? How about this approach? Compiler. Oh, you're right. When you're right, you're right. That compiler, man, knows what's up. All right. Okay. Actually, what's going on there? Wait, what? Hmm. Okay. Huh. What is going on here? Can I not? Oh, I know. Ah, that's of course. Okay. Yeah. It's not that subtle. It's a little subtle. It's not that subtle. That's a mistake on my part. Okay, now it's wrong though. But now it's wrong. Okay. Uh-huh. It's because I did not refactor my indices correctly. Yeah, I did a whole bunch of changing things there. Okay. All right. So this is maybe a little bit more space efficient. Could just modify the matrix directly. It's probably even easier than the other ideas that I had here. Oh, it's wrong now though. Oh no, hide it, hide it. Oh, that's a rough one. Oh no, what happened? Oh, that's not good. Uh-oh. Uh-oh. Oh, what did I do? What did I do? Oh, that's not good. Whoops. Oh. Huh. Huh. What? Uh-oh. Uh-oh. Oh, it's because I sorted it. Oh, that's the problem. Oh, that's subtle. Oh, that's really subtle. Ooh. Whoops. I see the issue. Okay. Oh boy. Tisk, tisk, tisk. So I do need... No, there's a problem. There's a problem. Oh, wait. There's a problem here. Oh. Okay. Yeah. All right. I was like, no. Whoops. Well, as long as, well, as long as the first pass accumulates the heights and the second pass forms the sorting each row, then it will work. I mistakenly tried to sort immediately after accumulation, which causes issues for the next accumulation. Whoops. That's a mistake, huh? Yeah, okay. Mistakes were made. Mistakes were made. Oh, that's awkward, huh? All right, let's try it again. Okay. So I think we just say, yeah, this is fine. And then just do this separately. Okay. Oof, man, oof. Oh, there we go. Now it's correct. All right. That was, oops. That was a big oops there, man. All right. I spent so much time on this question. Oh my gosh, the buffering is brutal. It's not much faster either. But it does avoid the thread local storage. Interesting. It's fast, but maybe not the fastest. Critical bug. Whoops. Huh. Okay, well, that's not true. I'm looking for micro optimizations. What might you suggest? Wondering if I should dump entire matrix into a different data structure first in order to avoid tracing. 3 passes? I don't know, man. I don't know. 3 passes seems crazy. Seems ludicrous. That's probably the only thing I could think of here that could be useful. Classic micro optimization to eliminate pointer chasing and improve cache locality. Yeah. Likely not contiguous in memory. Right, row by row. Might jump around in RAM, causing cache misses. Mm-hmm. Yeah. Can still optimize the processing. Copy costs might outweigh the gain. Hmm. Um, I suspect the pointer chasing is significant. In the average large test case, it'll be square root of 100,000 pointer chases. Would be something like, what is that? 300. 300 rows. Um, no, maybe not. I don't know. It's hard to say. It's hard to say. Hmm. Yeah, extra copying probably weighs the benefit here. Granted, may assist with cache. Overall, that doesn't seem. Hmm. Okay, 7 milliseconds is pretty good. I think there's got to be a slightly faster way to do this. Hmm. Actually, I'm not using. Peak micro optimization. It's pretty it's close, man. It's super close. Gold standard. Okay. So using counting sort here may not best. What do you think? I was thinking about trying to use counting sort. Problem with that is that it could be a problem. Hmm. Yeah, I think stud sort is actually faster. That's what I was thinking. Well, I could optimize. Well, I can optimize to modify the frequency amount. Relative ease doesn't incur extra costs. Element changes. Just update frequency amount. However, part that becomes yeah, O of m times m could be too big. That was the issue I was running into before. I was going to do this counting sort first, but yeah. Yeah, I still have to process the heights in descending order, which I Gotta go through the frequency array. Far too slow, yeah. It's fast, only if m is small. This is consistent regardless. Maybe use a hybrid approach in order to optimize further. If m is small, can switch to modified approach. Counting sort. If not, however, stick what I have. Do you think? Maybe that's a good idea. Oops. That might push the solution into theoretically sound, high performance sorting libraries work. Counting sort only outperforms to sort when n is large. K is small. Counting sort wins here. Okay. Yeah, so counting sort would be a lot faster than the wide matrix. Tall matrix. So stood sort is much faster. Okay. Squarish. So for wide or squarish matrices, counting sort's quite a bit faster. For tall matrices, stood sort is a lot faster. Okay, hold on. 8 milliseconds. I got 7 milliseconds before. Okay, hold on. Let's see. It's able to follow me here. Follow my reasoning. Still buffering, man. Super hardcore buffering. Dang. Brutal buffering. Okay. Next level of micro-optimization for this problem. Okay. Oh, that's funny. Oh, boy. First row. Okay. Yeah. Jeez. Huh. Interesting. Oh, I got it. Looks like we can move on. I got it anyway, 3 milliseconds. I was gonna say if I just keep rolling, I'll eventually get it. That's pretty funny. Let's actually try this though. So let's switch between counting sort and instant sort. If m is less than n, so we're going to use this one. Yeah. Otherwise, we're going to use counting sort. Oops, it's not that. It's going to be as simple as. Okay. So let's say auto frequency is going to be matrix of 0. And we're going to say frequency of 0 or frequency of 1 is going to be the percent. So initialize the frequency there. And then we're actually going to combine these together now. These can be combined now, as it turns out. It's a little bit different using the frequency, using a counting sort. So we say this next row, you get the previous row, which is going to be frequency. It's fine. Oh. Slight issue there. Never mind. We'll go back. We'll do it in parts. Okay, never mind. We'll do it two passes then. Never mind. Okay, so I'm gonna put the frequency map here. subtlety here as well. Slightly here. Okay. Okay. That's a subtle. There are some subtleties here, very slight. Okay, so we would say, I mean, man, that's a little bit complicated, isn't it? Yeah, that's a little more complicated for sure. Let me see, we're still buffering. Kind of, yeah. Still buffering a lot. Yeah, actually, this is kind of tricky. Not that easy to reuse the first row. No. No. Shucks. Hmm. Um. Excuse. Well, maybe. Thinking about it now. Thinking about it. Uh, I mean, this is kind of tricky. don't know about this. This seems a bit odd. No. Could do K instead of J to kind of keep things a little more clear. I mean, I don't know about this, man. This seems weird. This seems a bit odd. How's the buffering doing here? Still kind of a lot of buffering. It's a lot of buffering. Spent a lot of time in this question too. Okay. Wrong answer. Okay. So M is less than or equal to N. I think all of these fall into that case. Yeah. Okay. Results. Okay. Oh. Yeah. There is a subtle thing here. Yeah, it's kind of subtle. I don't know if this is going to be correct, though. I don't know. Let's see. Yeah, it's not buffering as much as it was before. Still having some buffering issues. Oh, look at that. There we go. Isn't that so much faster? Look at that. 100%. There we go. That's what we're looking for. Ah, there we go. There we go. That's fast. That's fast. I guess it's not always the fastest, but it's pretty fast. Yeah, the other solutions a couple times now I got 100%. So it's pretty good. There, oh, 1 millisecond. Oh, that's what I'd like to see. There we go. That's great. There we go. Oh, okay. Okay. All right, give me a moment here. Yeah. So, all right. But yeah, it's definitely much better. 1 millisecond's definitely very good. I'm gonna roll one more time. Didn't quite get 0 milliseconds, but 1 millisecond's pretty good. Bouncing around, it bounces around a bunch, but still is a super fast solution overall. Let me go ahead and move on to the next question. So that was for number 1727. So I spent a lot of time on this question, but it's an interesting question, and I kind of got hung up on it before. Let me just do one thing here before I get into the next one. Let me read this one, and then we'll go on the next one here. Number of common factors given two positive integers a and b. Turn the number of common factors of a and b. An integer x is a common factor of a and b if x divides both a and b. The number of common factors. Oh, that's interesting. Huh. How big are these? Yeah, less than 1,000. That's not too hard. We'll come back to this in a moment. This isn't too difficult. Let me just give me 1 second. Okay. So, yeah, unfortunately, a lot of buffering, but not the worst thing in the world. This question is kind of has a lot to do, has something to do with prime factorization. So let me keep it simple and just do I is 1, I is less than 1,000, plus I, and I is less than or equal to A, and I is less than or equal to B. I actually could just do that. That's fine. We're just going to say result 0 plus equals A modulo equals 0 and B modulo I 0 and return the result. Okay. How are we doing here? It's a lot of buffering. It's just a like mega buffering over here. Okay. Yeah, there's not much to say about this one. There are more sophisticated ways to do that, but the problem with all that is you run into prime factorization issues there. It's fine to just rely on the constraints to get the fast solution. Okay, n by n matrix of distinct numbers return all lucky numbers in the matrix in any order. A lucky number is an element of the matrix such that it is the minimum element of it in its row and maximum in its column. Okay. All right. So the minimum and the maximum of its row and its column. Okay. Yeah. I mean, straightforward thing. What are the bounds on M and N? 50. Okay. Yeah. I mean, are these what the minimums of the rows and the maximum of the columns? Let me see. Minimums of the rows, maximum columns. That's still a lot of buffering, unfortunately. Yeah, it's crazy amount of buffering, man. Gosh, what's going on? Give me a moment here. I want to test something. This is kind of nuts. Hold on a minute. Something's not right here. It's been doing this for a while now. Give me like a couple of minutes. So I think for this question, just to be clear, it is, what's the word? Sorry, my mind is elsewhere. Oh, so many things I gotta deal with. It's hard. It's hard to do all this stuff coming at you. Too many things coming at me at once. No. What's I even saying? Oh. Okay, it's hard to keep track of everything. Yeah, the buffering is brutal though. Buffering's no fun. What am I thinking of? We're looking at. What is this question again? It's something about. Oh yeah, the minimum is the maximum. So I probably will want to. Oh yeah, that's rough, dude. Holy smokes. Okay. Yeah, that's a rough one. Okay. Interesting. Okay. That would be why this buffering is so hard. It's just running a diagnostic to get an idea of what's going on. Yeah, that's very rough. Okay, so you're mostly just gonna be able to listen to my voice. So for something like this, I think just a simple, I'm not even sure if it matters for thread local. I think we'll just use int, just constant matrix size, n is matrix of 0 size. And then we're going to use int min column vowels, or just column vowels. Yeah, min columns of how many there are. It's going to be m is the rows and n is the columns. And then something very similar, max rows. Should probably be able to do this quite faster. Rows, and we're going to say for each column, so int I is 0, I is less than the number for each. So we do the rows a little bit easier. So max rows of I is going to be equal to std max element of matrix to the row, matrix of I, row dot begin, row dot end, and then I0 is less than n. We do column by column. Do int min val, do numeric limits. I have to check. Actually, I could just check it. I'm pretty sure it's just 0. We don't need the numeric limits. Yeah, it could just do 0. Oh, they said these are distinct. That's awkward. I don't know if it matters. It's going to be a similar kind of a calculation anyway. It probably simplifies things a little bit, but it's fine. So this is going to be each, yeah, it's going to be kind of flipped around. Min val equals just a min val, and matrix of ij. So it's really ji. That's the thing that's kind of weird here. This isn't going to be row by row. This is column by column. And then we would say min columns of I equals min val. And then we just do simple I is 0, I is less than m, I, increment I, j is 0, j is less than n, increment j. And then we just say results. This is like a lot of extra typing for this question. There are other ways to do this, but this is probably the simplest. Matrix of ij, let's do So val is min columns of I, and val is max rows. I think I did that wrong. I is the row, and j is the column. Let's give this a shot, see how that goes. See how we're doing with buffering. It's still buffering. Compiler error, right? A variable sized object may not be initialized. Shucks. Shucks. Okay. It's not the worst. Min columns, just a vector in columns. Kind of forget sometimes which ones can be initialized and which ones cannot. Yeah. Yeah, for small m and n, I think it's fine to just initialize the vectors. Oh, wait a minute. Oh, we want all the lucky numbers. Oh, okay, excuse me. Whoops. Okay. All right. I think you can at most have a 50. Pretty sure it's at most 50. Could be wrong about that. So if, then result back. Yeah, let's see. Wrong, of course. Minimum element in the row, maximum column. Did I get this wrong? Min row, max column. Oh, I did get that wrong. Okay. Min row, max column. Okay. Slight mistake there. Okay, let's try it again. Compiler. Okay. Maybe one more compiler, so refactoring. Oh, there we go. Okay, let's go for it. Okay. That took a while. Yeah, I mean, okay. Yeah, there's not much to say about that. That's pretty, you kind of just go, it's very straightforward, that approach. It's only a 50 by 50 array. It's going to be really, a 50 by 50 matrix is very simple. Integer array nums, greatest common divisor of the smallest number and the largest number in nums. That's it. GCD of the smallest and larger. So if you couldn't use the GCD function, you could write your own GCD function, which is just writing your own is just going to be the Euclidean algorithm, which is very straightforward. But we're going to use the GCD, so we're going to just do constant min-val. Could do min and max in one shot here too, but it's not really necessary. Although this is a very good application for that. This would be like the exact application for that, quite frankly. Okay. Yeah, still a lot of buffering. Okay. Buffering's brutal. Yeah, it's just a small test case. Yeah, it's fine. Okay, keep going. Sum of unique elements. Okay, integer array nums. The unique elements of an array or the elements that appear exactly once in the array. Sum of all the unique elements. All right. It's only from 1 to 100, so I can just do very simple. Just full peers here once, or just appear once, not appear once, or once, or one, false, and actually, let's do frequency. It's easier. Let's do frequency. There are a few ways to do this, but this is probably the easiest way. Okay. Frequency is only 1, then we can just add 1. Okay. Interesting. Buffering is pretty bad still. Okay. I think, it's wrong. Okay. All the unique elements. 1, 2, 3, 2. Is it 1 and 3? That's what. Oh, I see. Yeah, you can do it this way. Slight mistake on my part. Let's see if this is correct or not. Oh boy. Okay. Yeah, that's fine. It's fine. There are other ways to do this, but this works out okay. This works reasonably well. Yeah, still having issues with buffering. Okay. Minimum number of pushes to type word 2. You're given a string word containing lowercase English letters. Telephone keypads have keys mapped with distinct collections of lowercase English letters. It can be used to form words by pushing them. For example, the key 2 is mapped with ABC. We need to push key 1 time to type A, 2 times for B, 3 times for C. How to remap the keys numbered 2 to 9 to distinct collections of letters. The keys can be remapped to any amount of letters, but each letter must be mapped exactly 1 key. You need to find the minimum number of times the keys will be pushed to type the string word. Return the minimum number of pushes needed to type word after remapping the keys. Example mapping of letters to keys in a telephone keypad is given below. Note that 1 asterisk ampersand asterisk pound symbol and 0 do not map to any letters. 1 asterisk pound and 0 do not map to any letters. Okay. Oh no. What happened here? Uh-oh. Well, let's see. Oh my gosh. Talk about buffering. Some crazy buffering going on. Turn the minimum number of pushes needed to type word after remapping the keys. Example. At least you can kind of see what I'm doing. Jeez. All right. Interesting. So, what do we have here? Okay. So example 1. I've got this mapping here. The word is A, B, C, D, E. Remapped keypad given the image provides the minimum cost. A, B, C, D, E. Okay. Interesting. Okay. Huh. Then another example. XYZ, 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 XYZ. And do XYZ and then a whole bunch of other stuff. Okay. Oh, wait a minute. 1 push, 2, 3, 4, 5, 6. Oh yeah, 1 push for X 4 times, 1 push for Y 4 times, 1 push for Z 4 times. Okay. So interesting. A, B, C, D, E, F, G, H, I, 24. So there are. Can 1 be remapped? No, it's only 2 through 9. It could be remapped. Okay. Okay, so 2 through 9 is 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8. So I have 8 buttons to work with here. Basically, we're going to create a frequency map of the letters in the word. I'll come back to this in a moment. More or less a greedy approach is the way to, oh wow. Okay. Could be 100,000. Yeah, I'm going to use a frequency map for the letters. So the most frequent letters are going to be the first 8 of them are going to show up first. Second most frequent letters show up second, and so on. The question is, there are 26 letters, so we could do 8 of the most frequent, 8 of the next most frequent gets 2 multiplied by 2, 8 again, the third is 24, and then the last 2 letters, least frequent letters, are going to be, who would say 1, 2, 3? We're going to be pushed fourth. Question with that is, I think that's optimal. Yeah, that's the idea. I'm trying to figure out whether or not that's optimal. I think that's optimal. Yeah, if you move any of the more frequent or less frequent elements around in that sequence, you're just going to get a larger number. So yeah, that's optimal. Not easy to explain that or express that. That's basically it. Oh man. Uh-oh. Did we crash? Okay, how are we doing here? May need to restart stream. Oh boy. Let's see. How are we doing? Did the stream die? Mapping of letters. Let's see. To key express that. That's basically it. Okay, are we still live? Oh man. Uh-oh. Did we crash? Okay. Oh, we might be. Okay, how are we doing here? May need to restart stream. Oh boy. Let's Let's see. How are we doing? Mapping of letters. Uh-oh. Uh-oh. To key express that. That's basically it. Okay, are we still live? Oh man. Uh-oh. Did we crash? I'm gonna try one more time. Ah. Okay. Oh my gosh, man. Did the stream die? Hello, hello, hello. Did we crash? I'm gonna try one more time. Ah. Okay. Oh my gosh, man. Did the stream die? Hello, hello, hello. Did we? I'm gonna try one more time. All right, I think it's live, but it's just. Oh my god, dude. Ah, that is some serious buffering. That is some brutal buffering. Okay. All right. Anyway, so it's gonna be frequency map. We're gonna use word int frequency 26 0 for each character. I might stop the stream here. I don't know. I'm tempted to. This is a brutal amount of buffering. And now we're gonna say int I is 25. Or no, we're gonna sort. Excuse me, frequency. Let's see, plus 26. And then we're gonna go from the most frequent. Let's actually do backwards. And the result is gonna be I equals 0. We're gonna do result plus equals stood accumulate frequency equals 8. Then we're gonna do 2 times frequency plus 8 to frequency plus 16. Then frequency plus 16, frequency plus 24 times 3. And the last one is going to be frequency times 20 plus 24, frequency plus 26 times 4. This is basically the solution. All right. So still pretty brutal with regard to buffering. I'm going to submit this one. Let me see if stream is okay here. Stream is having a hard time. Okay. Not the fastest solution, but pretty fast overall. A little bit surprised. A little surprised it's not the fastest. It should be pretty fast. Should be really fast, actually. It should be about as fast as it gets. Surprised it's not faster. Gonna that's kind of annoying. Should be fast. I don't know. Huh. I'm annoyed. I'm annoyed it's not so the fastest. All right, I'm gonna ask the AI if there's anything here I'm missing. Is there anything, any micro optimization I can make this 100%? Let's see. Yeah, it's a little slower than the other solutions for some reason. I don't know. It's a pretty fast solution overall, though. I don't know why. There we go. Okay, got it. All right. As long as I get the 100%, then we were in good shape. Okay. A few micro optimizations. Okay. Manual loop. Okay. Counting sort logic. Extremely fast. Manual selection of the top elements, simply relying on the highly optimized loop fusion. Hmm. Hmm. I divided by 8 plus 1 times frequency. It's faster than multiple. Okay. It's using loop fusion. All right. Okay. Let me actually go back to that. Interesting. Loop fusion is what they said. Oh, no, not that. Okay, let me. Oh, shit. Excuse my French. Excuse my language. Okay. Okay. Go try the loop fusion, see what happens. All right. So they said just use a raw loop. Okay. Oh, all right. So I divided by 8 plus 1. So when I is 0 through 7, get 1. 8 through 15, you get 2 and 16 through 23, you get 3, and then 24 and 25, you get 4. Yeah, okay. That's fine. So it's going to optimize this out. Okay. It'll optimize the division by 8. It's probably as 3-bit shifts to the right. Yeah, I mean, it's just buffering the entire time. Okay, that's great. It's just buffering the entire time. Oh my goodness. And by great, I mean, it's not great. Oh, okay, so this was also 100%. So this was faster, it seems. This reached 100%, very quickly. Kind of surprised. I think that the main issue would be the frequency map in the first place. Added the loop fusion. Code is still fast. However, since the test cases guess the bulk of the code. So there isn't much room. Yeah, I would think actually this doesn't matter that much. The loop fusion. Unroll by 4. Unroll the loop. Huh. Okay. Yeah, this is probably about as fast as it goes. Okay. Interesting. All right, we'll keep going. Yes, actually, it's kind of silly. I'm trying to, not silly, but the speed up isn't going to come from, the speed up isn't going to come from, like loop fusion or modifying that portion of the code because it represents a much smaller section of it. All right, how are we doing here? Yeah, brutal, absolutely brutal. What's the word for that? Absolutely brutal buffering I'm dealing with here. Delete greatest value in each row, given n by n matrix grid consisting of positive integers. Perform the following operation until grid becomes empty. Delete the element with the greatest value from each row. If multiple such elements exist, delete any of them. Add the maximum of deleted elements to the answer. Delete greatest value in each row. And my end matrix consisting of positive integers. Add the maximum of deleted elements to the answer. Number of columns decreases by 1 after each operation. Delete any of them? All of them, one of them, any of them? Not sure what that means. Answer after performing the operations described above. Add the maximum of deleted elements to the answer. Element with the greatest value from each row. Excuse me. So 3, 4, then 3, 2, then 1, 1. Doesn't this just remove every element? I'm pretty confused by this. I think this is just the sum over the grid. I don't know. Okay. Could be wrong about this, but I think this is as simple as just taking the sum over the sum over the I'm wrong. I don't know. I'm not sure what's going on with this. Yeah, that is some brutal. What is going on? Oh, that is some brutal. What's the word for that? Brutal. What's the term? Apparently this is wrong. Oh, excuse me. I gotta get the largest one each time. I'm sorry. I made a mistake. Oh, I see. Is it the 4? At 4. Okay. All right, never mind. I was gonna say, I was like, isn't this? Never mind. Never mind. Slightly more sophisticated, but still not that crazy. So sort the row. Start by sorting the rows. And then we're gonna go column by column. Column. Oh boy. Great disappointment. It's great disappointment. Sorry, think about something funny that I saw the other day. There was something really funny the other day. When I was watching. I think these are in positive numbers. Not quite sure how this question's supposed to work, but I think I understand. Yeah. It's something like this. Okay, so a little bit better in terms of throttling, but still getting throttled, not throttled. I'm pretty sure it's getting throttled, but the other word is buffering. Yeah, it's extreme buffering. Throttling and buffering, no fun. No fun. I'm gonna go for it. I don't know if this is correct. I didn't quite understand the question. Okay, it's fine. All right, that was right. Yeah, 100%. Okay, it's fine. We'll just keep going. Just keep going. All right, how are we doing on time? I might take a break. I think it's been 2 hours. I think it's just a good spot to stop.